Chroma is Wednesday, May 8th, and the fashion show is Friday, May 10th. So I hope you guys can come back and see what we have there. This fall, again celebrating the 140th, we have CCAD grads in the gallery celebrating 140 years of creative excellence. Community galleries all through the Columbus area are going to be featuring our alums. So it's going to be sort of a citywide celebration of CCAD. A few other upcoming events. We have the Spring Art Fair this Saturday, August, wow, heading into summer. April 6th, and our MFA and MDes thesis exhibition is opening tomorrow evening. Speaking of which, if you're interested in our Masters of Design program, we are still accepting applications. We do have a calendar of events outside if you haven't picked one up. There are still a few things happening this spring. So there is a brochure on the table, extra 3D glasses. Bevil calls them filters. So, but there are extra glasses out there, but also that's where you're gonna find the spring events as well as a survey about our audience. So if you have time before you leave, if you could fill out the audience survey, that would be wonderful. It helps us with our funding. We get a great deal of funding from the community, including the Greater Columbus Arts Council, the Ohio Arts Council, and the Skestos Endowment for Visiting Artists and Lectures, and CD 102.5. Now I'm going to turn things over to Assistant Professor Andrew McCauley, who's going to introduce tonight's speaker. Thank you very much for being here.
Do I have to stand on the side of the podium?
That was my tech.
Okay. I'm just kidding. Thank you, Dean Taggart, Dean Julie Taggart of Studio Arts. We're thrilled to have Dr. Bevil Conway here tonight. Dr. Conway is an artist and a neuroscientist who specializes in visual perception, often exploring the limitations of the visual systems in his own artwork. Dr. Conway is a native of Zimbabwe and a transplant first to Canada and then to the US. Dr. Conway completed his undergraduate training in biology at McGill University before earning a Master's of Medical Science at Harvard Medical School and a PhD in neurobiology at Harvard University. Dr. Conway has held positions at the Kathmandu University Medical School in Nepal, where he served as the Director of Education for Physiology and Pathophysiology at Harvard Medical School as a lecturer on neurobiology, at Wellesley College as Associate Professor of Neuroscience, and at MIT as Principal Research Scientist. Dr. Conway has received fellowships from the Alexander von Humboldt Foundation at the University of Bremen and the Radcliffe Institute for Advanced Study at Harvard. I got through all of that.
Wow. Me too.
So please join me in welcoming Dr. Bevil Conway.
Okay, so you'll notice I wore a jacket because I want to show respect. But if it's okay, I'm not going to take it off because it's too hot. Is that all right? Don't be offended. Okay, you can picture me with a jacket. All right. So so yeah, freedom finally. So it's so awesome to be back at CCAD. I have a very big, special place in my heart for this place, in part because I just love artists. I am one, and I love talking to artists, and the questions that I get when I come to CCAD are always like the best questions ever. So hopefully I'll make it through to the end, and we'll be able to have a little chat, and I'll stick around as long as Julie will let me. Okay, so we're just going to play a little game to start with. I want you to tell me what the medium is of each of these pictures. Ready? Let's see. This is going to work. Oh, there. First one. This is a Matisse. What is that? It's actually an oil painting. It's an oil painting. What's that? Oh my goodness, you're already asleep? People. This is David Hockney's first etching ever that he made in art school. It's an etching. That is a Conte drawing by Egon Schiele. And that's a watercolor by me. It's just a little detail. And that's a glass and silk box by me, a photograph. And that, does anyone know where that is? Tuttle Park, yes, that's in your backyard. All right, so this is a little collection of images, and each of them are art. I think we could all agree that they're art, and they're each in a medium. And a medium is it's the way in which we encode, store, and transmit information. And you pick a given medium in some way, in some sense, to shape how you're going to represent that information, right? It's intentional. You don't use an etching if you want a video, right? You're using a video because it's a video. And part of making art is figuring out what the right medium is to communicate and to encode, store, and transmit that information. And the theme of my talk today is that the brain is really the original medium. It's the way in which we encode, store, and transmit information. And if there's one thing that I want to do today, it's to try and shift the focus around so that we start to unpack a little bit about how the brain works, and then see the ways in which the way it works impacts the kinds of choices that artists make. And for me, what's super exciting is to then look at what artists are doing to try and understand something about how the brain works. It was this kind of spirit that led to this course that I taught at Wellesley College for about 10 years called Vision and Art. And in this course, we had lab exercises. The students got science credit, and all the labs were done in studio, making stuff and then examining how the impact of what you make reflects the kind of internal processes taking place that transmit light information into images. Okay, so I have 4 chapters this evening, and the first chapter is eye movements. So on the left-hand side is the biology, and on the right-hand side is the kind of behavior or the impact. So we're going to first talk about eye movements and the role of eye movements on looking behavior. Okay. So this is a fundoscopic picture looking down the back of your eye. And when you go to the optometrist and they dilate your pupil, then they shine light into your eye, that's the picture they see if you have normal, healthy eyes. And you can see right away that the retina at the back of your eye is not uniform. It doesn't look the same everywhere. In fact, there's a giant gaping hole right there called the optic nerve. The fovea, which is that little brownie spot, that's the spot that corresponds to the center of gaze. And you can see right away there's something very special about the fovea. That is, it doesn't have blood vessels in front of it. So you normally have blood vessels that go over your eye to keep your tissue nice and healthy. And at the fovea, what happens is the blood vessels form their fine capillary beds right there with their fingertips to give it lots of nutrition, but it keeps the big blood vessels away because you don't want a mask. You don't want them sitting in like a telephone pole in front of the part of gaze that you actually use. Your optic nerve, on the other hand, there are no photoreceptors there, and that's your blind spot. And if you haven't discovered your own blind spot and witnessed it, then look up on the internet how to do that. It's super cool and fun, and if I were here for longer, we'd do it all together now. Okay, so the consequence of that inhomogeneity on your retina is that you have to move your eyes. So my partner teaches music, and everyone's like, oh, that's so cool. He teaches music, and you teach vision. That's like what he does is in time, and what you do is in space. Isn't that like so exciting? And I'm always like, vision is in time. Like, if there's one thing vision is, it's in time. It's a miracle that you think it's in space, but you're moving your eyes constantly. In fact, to read any word longer than about 3 or 4 letters, you have to move your eyes across it and hold what you just saw in mind while you then read the... How does the brain work in order to be able to do that, to then give you the impression that vision is in space? I mean, that is a miracle, right? And it's a miracle that you know when you're a painter because you don't get the picture right away. It isn't like it just happened, unless you're a photographer, right? As a painter, you have to like start to do stuff. So this interacts with this inhomogeneity on your retina. And I call it the practice of making a picture, vision and the practice of making a picture. You're actually making decisions through the time it takes you to make the picture, and those decisions are influenced by the inhomogeneity on your retina, whether or not you know it or not. And you can see it reflected, I think, very acutely in this drawing by Matisse. It's a pen and ink drawing, where he's actually tracing out his eye movements with his pen. And as a result of the particular light contrast on the model, where the lightest light is on that left-hand edge, that's where he spends most of his time looking. And he's just encoding it like this, drawing over and over and over again to capture that eye movement. So this is a picture that shows the visual field scaled for acuity. So if you were to center your gaze right in the very center of it, it's about, each of the letters is scaled to be about as big as they need to be so that all of them are equally readable. So now when you look across that picture, you can see how how much heterogeneity there is across the visual field. Like basically moving about 3 or 4 thumbnail widths outside of your fovea, your center of gaze, your visual acuity plummets. But that doesn't mean that your peripheral vision isn't really good for stuff. It's good for a lot of things, just not the things you think of when you think of vision. So this is a painting by Matisse. Another one, we'll see there are a few artists that crop up again and again, and it's just because they're examples that are readily available. But in this particular picture, I like to think about where it is that I'm looking when I look at the picture. Because that inhomogeneity across your retina is guiding you when you make a picture, but he's also intentionally manipulating the scale of the marks to guide your viewer's eye through the picture. And so in this particular picture, most people will look first at that grid at the very back, and then they might notice that there's a figure off to the left, and their eye might dance around. If you compare the scale of the regions with this visual acuity map, you can see he's matched it almost perfectly, such that at the very center, that's where he wants you to look. They're very fine marks, and then they get bigger and bigger and bigger as you move to the periphery. And that's kind of amazing because that probably wasn't true if you were to sit there and encode the data as they were in the natural scene. This is a consequence of him turning that into a picture that he wants someone else to look at. Here he's done it again with this picture of anemones. He's got the very fine little marks that make up the flowers. And then the intermediate stage, he's got the pillow with the marks that are a little coarser. And then in the far periphery with that wallpaper where he's just got a big field. He's telling you in no uncertain terms where to look in the picture. And this is another one that I really like. It's this reader on a black background. It was painted in 1939. And I find when I look at this picture, I look first at the daisies and then at the woman's face. And then when I'm looking at the woman's face, I feel a little uneasiness because I'm not looking at the daisies anymore, and I kind of bounce back and forth. And I think, and I don't think it's unreasonable to assert, that Matisse is doing this intentionally. It's capturing a little of that uncertainty at the time that he was making this picture, around the time of World War II. A lot of people say, well, where you look is just the very center of the picture. Well, that's just clearly not true. And Hockney plays with this beautifully in this painting, this series of 3 stitched together large 22 by 30 sheets of watercolor paper that he did in Iceland, where I find it amazing because the top painting has almost nothing in it. And I just imagine what it's like to paint that, where you're sitting there with your fovea looking at this going, I just have to keep painting. And when I actually had the pleasure of spending some time with Hockney. We had an afternoon in his studio, and I remember talking to him about that concern, which is how do you paint, in some sense, for a viewer, not to make everything interesting at the moment you're painting it. And he was like, it's easy, I just like painting, I could paint a door. This is a picture where he's done the opposite. He's made the focal point the thing of low spatial frequency, and the background with that little texture is the high spatial frequency. So he's actually trying to thwart that relationship. This is an image by Aud Oliva where she's trying to unpack the difference between foveal vision, the contribution that foveal and peripheral vision are making to your experience. So when you look at this picture, most people see it's Albert Einstein. The Albert Einstein is encoded with high spatial frequencies that you can readily experience at the center of gaze. The blurry bit in the background, you can sort of feel it's a little uneasy, And if you shrink the image, you reduce their spatial frequencies and you can have it then appear. That low spatial frequency information is available to your periphery, and it's really important for doing stuff like navigating or telling you if there's a shadow of a predator coming over you, and giving you information about emotions. So when you smile, those smiles are encoded not in the wrinkles, but in the very deep muscle that introduces a low spatial frequency mark on your face. And that, I remember learning that when in high school. It will be no shock to Julie to know that I did a lot of theater. And one of the reasons I really liked the theater is I got to wear makeup. And I remember putting on scads of makeup, and the director came by and said, "You've got it all wrong. The point of makeup is you shouldn't be able to see it." And I was like, "Well, then what's the point of makeup?" And I later sort of uncovered that what they mean is you shouldn't know it's there. It shouldn't be evident to you sort of consciously. What we're after is a kind of low spatial frequency encoding of that information, which is what you get in your periphery. Okay, and this tension of foveal vision and peripheral vision is of course something that artists know implicitly in their practice, and people like Chuck Close are deliberately trying to subvert that foveal information and the peripheral information here, where the foveal information is completely decoupled from the low spatial frequency elements that it then comprises to give you his self-portrait. This tension between foveal vision and peripheral vision is something that conceptual artists have played a lot with, and I love this series of works by John Baldessari, where he hired some scene painters to paint these scenes where he was just intentionally pointing at stuff. And what he's really doing is he's trying to uncover what is it that makes you pick what you pick when you paint. And that's a really kind of deep problem, because you're going to invest, if you're a painter, you're going to invest, I don't know, a week, a month, a year, 10 years on a painting. It's an unsettling decision what you're going to do, what you're going to set out to do. So Baldessari is unraveling that problem of where you look one step further into a kind of conceptual domain where he's saying this really influences, in some sense, why you pick what you pick. Okay, so that's chapter 1. Chapter 2 is the retina. Now we're actually hit the retina. We're going to encode that information in the retinal ganglion cells. So at the very back of your eye, you can think of the retina as a retinal cup. And across the retina, we call it the retinal sheet, there are photoreceptors that you can think of literally like eggs sitting in an egg cup, tiling the entire back of the eye. And the way the image gets projected onto the retina is just straightforward optics like in a camera. In order to transmit that light information into the brain, the photoreceptors have to turn that light energy into electrical impulses. And that's important because electricity is the currency of the nervous system. As you probably know, there are 4 types of photoreceptors at the back of the eye. There are 3 types of cone photoreceptors, and there's 1 type of rod photoreceptors. The cone photoreceptors are in charge of all aspects of vision that you think of when the lights are on. So they tell you about black and white, they tell you about motion, they tell you about faces and objects and color. They tell you everything you think of when you have vision. The rods, there's just 1 class of rods, and those only get activated when the light is dim enough. And you can think of the rods and the cones as kind of 2 scales, literally like scales for light, where the rods are very finely calibrated, so they can only measure things that are very small amounts of light. And if you step on them with too much light, you squash them and they don't work anymore. The cones, they're calibrated so that you need a fair amount of light to stand on them to get them to work. And I tell you all of this because a lot of people think that cones are for color and rods are for black and white, and that's just wrong. So if there's one bit of science you take away, please remember, cones are for everything. And we're going to talk a lot about cones in a later chapter today. So the very first stage in the retina is where the light information becomes pixelated, as it were, into this set of egg cups tiling the back of the retina. Those photoreceptors then talk to each other at the next stage. So there are cells that sit behind the photoreceptors that are connected. So I might be one cell that's connected to this photoreceptor, you, and also connected to you. And me, the downstream cell, I may be getting excited by you and inhibited when you're active. okay? So I'm starting to stitch together, in some sense, this information. I'm creating, as the brain, I'm creating information out of that retinal array. And that's when I talk about the medium of the brain, we're interested in how that active process happens. What are the choices that the nervous system makes in deciding what patterns of light that hit the retina it's going to encode? And the very first pattern of light that's encoded is simply local contrast. So there's two sets of cells across the brain that are right behind the photoreceptors. One set just looks at little dots of white. And if the dot of white becomes too big, the spot becomes too big, those cells drop out. They stop working. And there's a completely redundant set that responds to spots of black all across the visual field. So one cell responds to a spot of black here, another cell next to it responds to a spot of black there, and so on. So I have a whole tiling of the whole visual field with these two redundant spots that are in essence the basis for all vision. They are the antagonism, light and dark, that then get transmitted up to the cortex. And the spatial scale of those, that activity determines a lot about what we see. This is a recording done in that first step just behind the photoreceptors. And on the left-hand side, you can see the little spot of light. And on the right-hand side, you can see how much activity this cell showed. So with a tiny little spot, it showed a lot of activity. And then as you make the spot bigger and bigger, it showed slightly less activity. And then if you just put light in the surround, you can see it actually has a little dip of activity. It's actually suppressed. So vision, at its core, depends on local contrast. And that's why. There's nothing out there in the world that tells you that the lightest light should be next to the darkest dark. That happens because of the way the visual information is encoded in the retina. And people have played with this phenomenon to come up with fabulous demonstrations like this one. It's Hermann Grid's scintillating grid, where at the very center of gaze, you can see these little flickering blacks that come and go. It's because the scale of the grid is matched to that local contrast calculation to give you at a certain location in your periphery where the scale of those grids matches the size of the sampling of those retinal ganglion cells. It matches them perfectly to give you that illusory percept. And you chase it because your foveal cells, remember, have smaller receptive fields. They sample vision more finely. This local contrast calculation is evident everywhere, and it's something you become intimately familiar with when you make work. So instead of representing or being able to see gradual changes in gray value, what we see are these local boundaries. In this particular picture, that central disk, which everybody sees as being illuminated from the top as light on the top and dark on the bottom, is actually a uniform gray. It's the same gray throughout. The change is actually a gradual shift in the background, going from dark at the top to light at the bottom. And those of you who have played with Photoshop have done your own versions of this. For me, what's fascinating about it is it uncovers that very basic thing about how the visual system, at the first stage in processing, encodes that information. And artists have pushed this to extremes to compensate for the limitations of the medium that they're working in. For example, charcoal, which can never make things really bright because you're always sort of stuck within the gray of the paper. So how do you make that gray paper look really bright? Through a kind of chiaroscuro, through manipulating these local grays. This is a lovely drawing by Seurat. So that's chapter 2. Chapter 3, we're going to talk about the next stage of processing that happens, which is lines and edges. So the parts of your brain that are handling these local contrast bits, they're all in the retina. So the very first signals that the retina sends up to the brain are these local contrast calculations. Light on a dark background and dark on a light background, that pixelated picture of the world. Your primary visual cortex, which is situated, ironically, very far away from the eyes, as far away from the eyes as you can get in terms of the cortex. That primary visual cortex then listens in on those retinal signals and turns them into vision. And we're going to talk a little bit about how that happens. So this is a dissection of the ventral view of a human brain. They're not alive anymore. Okay. And what you're seeing here in white are the axons, the wires that connect the retina, the top, through the optic chiasm to the lateral geniculate nucleus, a little relay station in the middle of the brain, and then up to primary visual cortex. So these are the wires that connect up to primary visual cortex. And you can see them plugging into the cortical sheet back here. And it's this cortical sheet that does a lot of the heavy lifting of vision. So what do I mean by the cortical sheet? So you've probably seen a picture of the brain, or maybe some of you have even seen a real brain at some point. The big convoluted mass that sits on the top, and then there's the cerebellum underneath, which is the more finely folded one. We're just talking about the big one, the thing that you see most prominently when you look at the brain. That thing, what you're looking at, is the cerebral cortex. And the cerebral cortex just comes from the Greek word meaning rind, like a orange has a peel, that's the cortex. If you peeled open the cortex, if you peeled it all open and you stripped away all those wires, you could actually unfold the cortex and have a big sheet. And it's about 2.5 millimeters thick. And that sheet is the stuff that does all of the heavy lifting. And a bit of a brain over here that does some heavy lifting will talk to another bit of brain over here through these wires, through these axons that connect one bit to the other. So we're seeing in this picture those retinal ganglion cells connecting to the LGN cells, those wires carrying the retinal information up to primary visual cortex. And our question is, what's going on in primary visual cortex? Before we get there, I just want to point out one cool little thing. We have about 20% of your cerebral cortex involved in vision. Okay, so think about that massive tissue, all right? Look how big the optic nerve is. It's about 2.5 millimeters in diameter, maybe 3 millimeters in diameter. What's all that cortex doing with this tiny little tube that's giving it that information? It's like Morse code, where there's a few little things coming up, and then the cortex is like inventing a whole bunch of stuff. It's computing relationships between what that pattern of activity is. It's doing a lot of invention, of construction. And that's why neuroscientists like myself think of vision as a very active process that's synthesizing stuff from the retinal information. And one of the first things that the visual cortex synthesizes is edges and lines. So if you were to record in primary visual cortex from a neuron there, you listen in on one tiny little microscopic cell and you could listen to the electrical signals that it relays. Those cells respond, each cell responds specifically to only a given line of a given orientation in the visual field. And then sitting next to it is a cell that responds to a line of a different orientation. All of those cells in a given location in the cortex all represent the same little patch. They only see the same little piece of the visual field, but they have a redundant representation of that visual field, but all with different orientations. So the idea is that what the visual cortex is doing is a kind of data bank. It's got a whole bank of cells, each of which is tuned to a given orientation. And depending on what you look at, it activates some subset of those cells. So at any given time, you've probably heard only like 5% of your brain is active or some nonsense. Your brain is always active. It's just sometimes it's actively doing nothing. By which I mean, if there's a blank screen there, there's a bit of your brain that's saying, there's a blank screen there. Right? And that's, the white space is just as important as the dark, which I'll get to. So that's a picture of one of these cells, what it might be sensitive to. And the way it gets the sensitivity to that line of that orientation is by sampling, getting inputs from cells that have, in the visual field, that sequence of activation. So it's stitching together. Now there may be another cell that's got a different orientation, and it's also getting input from this one, but maybe from 2 other retinal ganglion cells. And in that way, the visual cortex is synthesizing this picture of the visual field. In fact, that picture, which is topographic on the cortex, is so good that you, with our modern day scanners now, I can put you in a scanner and I can read what you are looking at just by looking at that topographic representation of activity on the brain. I can in fact decode pretty accurately what kind of thing you're looking at, the words or pictures or scenes that you're looking at. Okay, so the importance of lines is reflected in, basically almost every graphical mark that we have history of, going right the way back to cave art. What I'm interested in is the ways in which artists acknowledge, understand the importance of lines, and then the ways they tweak it or manipulate it. So this is a very early drawing by Egon Schiele, done when he was 17, and it's of his sister. And you can see again, the parts of the visual image that he's looking at are the contours and edges. I think they're kind of overworked. I mean, it's not what I would call a brilliant drawing. It's probably an expensive drawing, but that's different from being a good drawing. Okay? Contrast that drawing with one of his later works, one you've seen earlier. Here what you see is this extraordinary restraint. Right? It's what he's actually doing is spending a lot of time not drawing stuff so that he creates a visual puzzle that invites you, as the viewer, your visual system to complete. So he's making your visual system an active participant in this dialogue of making an image. And it's underscored by, do you see the little gap on the woman's face? Like he sort of leaves this imaginary line. There's no way that that gap existed in the real picture. Like it was definitely completed. Right? But he leaves it out, he's like, I know what you want me to do is complete it all. Here it's like way overworked. In fact, surprisingly, that part of her cheek is the part that he has overworked the most. And then he leaves it blank. And he did this again. There's that same little region. I don't know, he's really obsessed with that little bit of her cheek or something. There it is again. I mean, you won't see an Egon Schiele drawing. He does this all the time. I love this one because the entire top of her head is like detached, right? You can see her as like floating off. The only thing that's holding her eyes to her body, as it were, is an imaginary line that depends on your visual system to hold it down, okay? Makes it an active and interesting drawing. And you can contrast that late Matisse drawing with this pen and ink drawing where Matisse is displaying the same kind of restraint. Okay, so now we're going to get to the last chapter, which is the longest chapter because it deals with color, which is what I'm obsessed with. Okay, so remember I told you that there are these rods and cones at the back of the eye, and which ones are the ones that are operating during normal vision? Cones. And what are the rods doing during normal daylight vision? Nothing. And what are the cones responsible for? Everything. Okay? They do motion, color, everything. Okay? So the question is, how does the brain take the activity of the three classes of cones and turn it into color? What is it doing? We've just seen how it turns it into edges, but how does it take that same activity and turn it into color? Okay. Well, one thing to appreciate is that there's lots of bits of brain that are responsible for vision. So as I said, that first stage, primary visual cortex, which in our infinite logic we call V1, visual cortex area 1. So I might refer to it as V1 because it's like my buddy. Okay, V1 is computing all those lines and edges and gets that retinal information right away. But primary visual cortex, it sends its signals to many different brain areas. And in fact, there are two major areas, or we can think of them as like sets of areas. One of them is the dorsal stream, which on me sort of starts at primary visual cortex way away from the eyes. It kind of goes like that, right over the ears, okay? And then there's another set of areas that receives activity from the eyes, from primary visual cortex, that goes in the ventral belly, right under the surface. I have to stick my fingers up in the back through my palate, touch it. These bits of brain handle visual signals in two very different ways. That dorsal bit, as in the dorsal fin, the top part, that gets basically only black and white information. It's considered much older cortex, primitive, lower evolution. Our evolutionary ancestors didn't have color vision like we do. They just had this bit. And that bit is responsible for seeing things moving, for like if I throw something at you, you'd be able to duck, signals related to attention, capturing attention for luminance contrast and so on. It also helps you navigate, know where you are in space. Okay? The ventral bit that sits on the ventral belly is responsible for all the stuff we think of as what is out there. So some people talk about that dorsal bit as like where stuff is, and the ventral bit as what is that. And that's cool because it's in fact a discovery that was made in computers. So in graphics, to represent a movie or a sequence of images, the most simple, computationally light way of doing that is to define the object, like this is an apple, and then give me a vector to say what I do with that. I threw it like this. And that's a heck of a lot easier than giving me a whole series of frames to define the pixels of that apple throughout space. And it turns out that the visual system invented that long before computer scientists did. Okay, so we're going to talk a little bit about the difference between these two bits of brain, but importantly, they hinge on a notion of value, of luminance contrast, because that's the signal that is encoded by that dorsal bit and not the ventral bit. And to artists, you already know this. So what is luminance contrast? It's the black value or the gray value you could associate with a given color. And every color has a luminance value. And in this picture, I've tried to match the luminance values of the colors on the left, on the right. And there's a curious feature, which is that yellow and white actually have about the same luminance value. In fact, yellow might even have a higher value than white, which is surprising because if you use yellow paint, you're actually taking away light, which makes it, in some sense, less energy, but it looks like it's got more energy. We don't understand that paradox, and it's one I'm really interested in. So I would like to understand that in neuroscientific terms and where it comes from. So it's that dorsal bit of brain responds to luminance contrast, and if you've got things that don't have luminance contrast in them, that are balanced for color, balanced for luminance, we would say they're equiluminance, they're equal gray value, that dorsal bit of brain can't see it. Okay? This is played on by artists regularly and designers. This is a picture by Larry Poons that the art historian, art critic Michael Fried described as, under the gallery's bright lights, the dots tend to flicker and jump and blink and flare until we begin to fear for our retinas, if not our minds. Okay, now you can, it's depending on the calibration of the projector, it may or may not be perfectly equiluminant, but you can make it definitely not equiluminant by introducing a color filter. So if you just look through the blue one and close one eye, you'll see that all the dots turn white and the background turns dark gray, and all of a sudden the dots don't jump around anymore. You notice that? And if you turn it around the other way, you can make the dots black, looking through the red filter, and now the dots stop moving because they're black, right? So what have we done? We've introduced a luminance contrast, so your dorsal stream can now see it, and it's not sitting there going, I don't know what's there, right? Sending this big error signal, which is interpreted when it is working to give you this flickering. Okay, so that dorsal stream is important for knowing where you are in space. When you look at this picture, which is made with equiluminant red and blue, through the color, look at it through the red filter, all of a sudden, now you have luminance contrast. You can experience the depth in the picture, and you actually get a little experience of vertigo. When you take it away, it flattens it, because your dorsal stream can't see it. Does that work for everybody? There's another one. This one you have to flip the filters. So now you look through the blue one. Doesn't work as well for me, but it's still pretty good. And there's another, this one works real well for me. Here's the blue filter. So that dorsal stream bit is colorblind. And if you encode information only in color, it can't see it, and it can't tell you about where you are in space. That's the simple answer. So luminance value is really important for telling you about structure in the world, which we'll talk about when we talk about Matisse and how he manipulated color. Monet knew this implicitly when he made this painting, which is a very famous painting called Impression Sunrise, where he's actually calibrated the gray value of the sun to be exactly matched to the gray value of the sky around it. And he does that in order to give it this kind of eerie, shimmery quality, okay, to give it that kind of feeling, really. And it's amazing because what he's doing here is he's not showing you what's hitting his retina. He's showing you what that feels like by manipulating, using the medium of the nervous system and the way the nervous system encodes information to transmit something more meaningful than he could with paint if he was just representing what's there. Okay, so that ventral part of the brain, my lab discovered, actually has 3 parallel bits of brain in it. One, this is the ventral surface. That's what your brain would look like if you got to peer under and see. So my eyes are pointing at the top and my back would be at the bottom. My feet are spread out towards you. That's the ventral belly of the brain. And you can see there are these 3 parallel tracks. One of them is responsible for faces. Another is responsible for color, processing color. And the more medial one is responsible for telling you about places, information about what the place is. Okay? My lab, we discovered that relationship. Other people have discovered that there were face patches and face areas, but we showed, no, there's the systematic relationship, which tells us something about how that bit of brain actually evolved. And the amazing thing is, if you have a stroke or a brain damage to any of these pieces of brain, you selectively impact your ability to experience that sense, that part of vision. So for example, a patient described by Oliver Sacks, who had carbon monoxide poisoning that caused damage to this middle bit here. He was a painter, and he actually described his experience very vividly. He said he saw people's flesh, his wife's flesh, his own flesh, as an abhorrent gray. So it's not colorless. I mean, it is colorless, but it's more than colorless. It's like lost the affective meaning of the color. Foods were disgusting in their grayish-dead appearance. The mental image of a tomato was as black as its appearance. I find that amazing because it tells us that the bits of brain that are responsible for computing color are also the bits of brain that are responsible for knowing and remembering and understanding color. There's nobody else looking at the brain telling you that. That is what this bit of brain is computing. And if you take it away, you lose that mental imagery. So how does the brain compute color? I want you to look through the red filter with only one eye and close the other eye. Okay? So do you see all the text is basically the same color now? It's all, what color would you say it is?
Red.
Really? It looks basically orange or maybe white, right? Now take away the red filter and what color is the text? Red. But now you can see that red is really very clearly red. Okay? This is called the paradox of Monge. When I put the red filter in front of my eyes, I would have thought that everything would look way redder because I'm now looking at the world through rosy-colored glasses, right? But paradoxically, it doesn't look redder. It actually looks less red, right? I look at the red text. The red of the red text looks less red through the red filter. That's crazy. That don't make no sense, right? And it doesn't make any sense because you have some picture in your head about how you think color works, where you think color works by simply a reflex between wavelength and report. And physicists have peddled this fake news for a long time, right? Long wavelength light we call red, and short wavelength light we call blue, and it's in the rainbow, and it's red, orange, yellow, green, blue, indigo, violet, and that's it, case closed, that's how you see color. That's what physicists tell you. It's the only part of the electromagnetic spectrum that is dependent on a subjective viewer. Everything else is like X-rays and gamma rays, perfectly objective. And then you get to this tiny little bit, 800 nanometers, where the physicists are like, that's red. And you're like, hang on a minute. It's only red because of something our brains do with that bit. It's dependent on us as an observer, and it's not even the wavelengths that are red. Okay? So how do you get color? Well, do the same trick here. It's the same idea. Look at the woman looking out of the window. What color is her garment? Again, it becomes way less red. Okay? What this tells us is that what actually makes something red is the same idea as what makes something black or white. It's contrast. It's its relationship to something else. And if you make everything red, then nothing's red. okay? So to make that dress looks red, you have to have lots of other not red around. And you know that as a painter, right? That's not rocket science. So it's sort of, in some sense, it's like, yeah, all right, I know where you're going with this. That's something I already knew. But we're not taught it in schools because physicists have like crooked us with STEM, right? And painters are like, no, I know something, and it's not physics. Physics doesn't tell you everything. Okay, your whole life, I know it's like one group therapy session. Okay, so contrast is super important. In fact, you can manipulate color so that it turns from one color to another. So I want you to tell me for the upper margin of the cube on the left, tell me the colors. So it starts with blue and then it's what? No, the upper front margin. Unless we all have color blindness. Blue, yellow, red, blue, green. Do you see that sequence? In the front top margin? Okay. On the other side, what are they? Blue. So you use the same color terms, you're perfectly happy. Now some of you, very cleverly, will say, well, that one's illuminated with a kind of yellowish cast, and that one's a kind of bluish cast, and I'd say, very good. But did you notice that that one and that one are physically identical? Okay, they're both gray, right? And that's crazy, because if you were setting out to paint that cube, I would have squeezed out blue paint, and Julie would have too. Okay? So what that tells you is that the way we get color is not by matching the stuff hitting our eye. It's by comparing it against everything else. And in that case, gray looks blue when it's surrounded by yellow, and gray looks yellow when it's surrounded by blue. So that local contrast is what gives it to you. Why are yellow and blue so special? Because they're the colors of natural lights. So direct sunlight has a lot of incandescence, got a lot of warmth in it. Blue sky has a lot of blue because of light scattering. And Monet knew this. That's why he paints his shadow literally with blue paint and the surround literally with yellow paint. Because those are the two main illuminants. And about, 10 years ago, I wrote a paper where I said, it's amazing because the visual system is actually adapted to those color statistics. So we walk around in the world with an idea in our heads about what the color of the light is. We either think it's blue light or we think it's yellow light, and we compensate, we color correct depending on what our assumptions about what that light is. So in the cube case, you clearly compensated for yellow because it's unambiguous, and here you clearly compensated for blue because it's unambiguous. That compensation, that prior that we have, that knowledge about the world, is embedded in everything we know about the world. It influences digital renderings so that if you are set to pick colors, you will not pick them uniformly. You will pick them biased by these colors, and this influences movie posters and basically every piece of artwork out there. You won't see a movie poster. And then about 4 years ago, I got a phone call close to the middle of the night from Adam Rogers at Wired, who said to me, Bevil, he's an old friend, and he said, Bevil, this image is trending on BuzzFeed and scientists have no idea what's going on. Tomorrow's going to be really weird, but right now the scientists say this is because of differences in rods and cones in the eye. Real legitimate scientists. I asked him to name names. He told me people I know and I have great respect for. And I was like, no. What do rods do during daylight? Nothing. This can't have anything to do with balances of rods and cones. And Adam was like, well, what is it? And I said, it's perfectly obvious. You carry around in your head an assumption about what the light is. You either think it's yellow or blue. And when you look at this, if you're one of the people that think the light is yellow, then you get rid of the little yellowy component here, and you make this into black, and you get rid of that, and you make it into blue. And if you think that the light is blue, you do the opposite. And in that way, I walk them through exactly what two different camps of people are doing. These people think the light is yellow in direct sunlight, and these people think the light is in shadow. And that's it. I was like, case closed. It's done. He was like, oh, that's clever. Okay. And he said, your tomorrow will not be the same. And I was like, it's going to be fine. Sure enough, my tomorrow was not the same. So you might not know this, but this image, the dress, is the most viral image in the history of the internet. Okay, still to this day. It was cross-cultural, it transcended all bounds. And the reason is that we have a really visceral sense of what color is. It's objective. Red light is long wavelength light. It's out there in the world. And our visual systems have worked really hard to convince us that color is meaningful because it's attached to something I can hold on to out there. And this picture tells you, there's no such reality. It's all in here. And that's very unsettling. And I have to show this because this was my moment of fame that my Wellesley undergrads were very proud of, where I even got a little figurine in the short news because I was all over the newspapers then. Okay, so brain cells determine color by subtracting local context. And the brain cells do it in a way by comparing very local chromatic interactions. So we gain some insight by measuring brain cells and seeing how local those interactions need to be. And I'm going to paint this against the opposite, the contrasting possibility, which is the yellow light is influencing everything, right? So maybe the brain cells are interpreting yellow everywhere, and in order to be able to do that discounting operation, I have to have yellow everywhere. The brain cells said, no, it's happening very locally, just like the white and the dark. So to test that, I put these little white buffers around this Elber's image, and you can recover then a stable percept of the image because you've obliterated those local contrast interactions. And I think it's super cool that this is a technique that people like Matisse and other artists have used in their own painting practice. So Matisse, in his late work, mature work, he would often leave little parts of the canvas blank. Now we know he didn't just run out of paint because he signed it, okay? And he was like, this is done. It caused huge ripples in the art historical community. And you can understand why, because at the moment he made this painting, pictures were not meant to represent anything about the maker. It was a view in the world. This thing is advertising that it's made of stuff. It's canvas and paint, deal with it, okay? Painting, French painting around this time was like a window in the world with a nymph, right? There's no illusion here that this is painted canvas. He has pulled apart the operation, the practice of making paintings to reveal in modernistic terms its own subjectivity. It's making the painting aware of itself. Okay? And he did that, I think, only because he cared so much about color. And he wasn't very good at figuring out how the color relationships would work out if he painted right next to each other. And so he didn't have to because of the explosion of new pigments. So he could get whatever color he wanted right out of the tube. And then his only game then was to figure out how he could keep that color from changing as he filled the rest of the canvas in. And he did it just by putting these little white buffers everywhere. Put the pictures up and was like, I have a nice picture that looks great. I can enjoy it sitting in an armchair. And that's a direct quote. And then everyone's like, no, this is earth-shattering. And he's like, no, it's not. It's just a beautiful painting. Okay? He did it. You won't see a Matisse painting again. He did this over and over and over again. It does not have to be white lines. Beckman showed it can be black lines. And the amazing thing is, as soon as you do this, you flatten the world. Why do you flatten the world when you prioritize color? Because remember, value information is dorsal. That's the stuff that tells you where stuff is. Color, as soon as you start prioritizing color, you flatten the world, you make it flat. And that flatness and the materiality, the legacy of that is, of course, the great abstract painters like Rothko, who ended up stripping everything of form until all you had was that material flatness. Okay, and there's another reason why I think these contrast things are so fun. If you've ever painted with paint by number kits, they work, because they take your visual system through that operation. So you're told to paint that in the cloud, and then when you do it, it doesn't look right. And when you finish, you're like, this is kind of neat. And you kind of watch your own visual system do this like backflip, okay? Of course, if you're me, you're told to paint that in the cloud, and you're like, that can't possibly be right because I know way more about color than they do, so you mix up your own color, and you put that in the cloud, and then when you finish, that doesn't look right, and you go back to the instructions, and then you get it right. Okay? And that's the game of painting. It's trial and error. The importance of white, I have 9 minutes, it says. The importance of white, I think, is underscored by this lovely exchange between Cézanne and his dealer, Vollard. So he finished this portrait, he handed it off to Vollard, and Vollard was like, it's not finished. There's this little bits of white showing everywhere. I want you to finish it. And Cézanne says to Vollard, maybe tomorrow I will be able to find the exact tone to cover up those spots. Don't you see, Monsieur Vollard, that if I put something there by guesswork, I might have to paint the whole canvas over, starting from that point. And I think that captures so directly the challenge we face in painting and the challenge the visual system faces in trying to structure or construct a representation of the world. Everything is related to everything else. If you push over here, it has an effect over here. Okay, and that's a painting where I played with some of these. In fact, this was a painting I had in a show before I did any of this work. So I wrote, some essays and did some research. This was the painting that got me going, where I had this painting in the show, and this art critic from MIT came by. She was like, your painting has a lot of air in it. And I was like, it's watercolor paper and watercolor. There's no air. I mean, it's like, what do you mean? And then it was like, what she means is there's all of this white space. And I was like, okay. And so I went back to studio and I didn't know about the Cézanne quote, and I started filling in all the white spaces. And we're like, it doesn't work anymore. And I was like, why isn't it working? How have other artists struggled with this problem? And then I went down this road of looking at Matisse paintings and thinking about the neurophysiology and so on. Okay, so the other piece of this that's important to appreciate is that the scale of this interaction that gives you color contrast is local, but it's a little bit coarser than the scale for black and white. And it has to be, because in order to get color, you've got to integrate those activity from 3 different cone types with 3 different spectral tunings. Whereas in black and white, you can just sample each one separately. Does that sort of make sense? Like at every location in your retina, you only have space for 1 photoreceptor. So to get color, to compare their activities, you've got to like pool a bunch of them together. And that necessarily means that color has lower spatial resolution than black and white. And this point was made very beautifully by Steve Chevelle, and I adapted it for this picture. So this isn't going to work here, but that blue is the same. The letters are only written in that turquoisey color or the orange. You can trace it through, do you see? The difference is there, it's next to yellow, so it's averaging with yellow, and there, it's next to purple, so it's averaging with purple, and vice versa for the red. So you just trace it over, you can see the power of this integration. I like this picture, my version of it, for another reason. So there, it's unfair to say the blue is the same in both locations of the because it's actually being mixed with something else. On the right-hand side, it's being mixed with purple, and in the middle, it's being mixed with yellow. Okay, so you're like averaging, right? But what's the color of the central O in the 2 O's? On the left, it's, what color would you say that is? Like yellow, and on the right, you would say it's more purple. But those are physically exactly the same, right? They look different because of the contrast created by the O surrounding it. So you have in this one picture both of these things, the small scale where you're averaging and the larger scale where you have contrast. And when you're painting, you've got to manipulate the scale of your marks and how far away your viewer is. And something I've discovered in my own work is that if I make a watercolor painting or any painting, it only works, as in I like it, it only works when I look at it at the distance I made it. And why? Because I'm matching the marks to work with my visual system. Right? Artists have known that for years. That's why when Matisse wanted to make a drawing, he wanted you to be able to see it as a he put it on a big stick, and he was like, I'll paint back here. Right? That's why. And if you shrink it, you get rid of that. And of course, pointillism played with that. Okay, so it's only after, I don't really like pointillism, can you tell? It's only after years that the young artist can touch color, not color used what does he say? Not color used descriptively, that is, but as a means of personal expression. So this is the great Matisse quote, and what he's saying is, to get the shape, you need to get the value. So here's a beautiful painting of this woman where he's captured even the little light on her nose underneath the shadow of her hat, but he does so using wild colors. So he can decouple the color to be expressive from the luminance to tell you what's there. And that is hard work. Last bit, then I'm done. Cognition. So we've talked a lot about these retinal signals and the medium of the brain handling the stuff coming to your eyes. But equally important is cognition, is what you're thinking about what you're seeing. And there's huge bits of brain, like your frontal cortex, this whole bit up here, that's involved in making predictions about what you're likely to be looking at or seeing or thinking. And scientists have spent a lot of time trying to work out what those predictions are. You've already seen one example of them. So it's not what you see is not just what's hitting your eyes, it's what you know about what you see. You've seen one example of that already. Decoupling this thing to explain the two different ways of seeing that image, that's about what you know. It's about what you think you know about the lighting. That's very much influencing what you see. But there are lots of other examples. This is a wonderful one I like from Stephen, aged 8 or 9. He had autism. It's a great picture because in this picture, it's like I can feel myself sitting in this cockpit, and it's a runway, and there are gears, and none of this is veridical in terms of perspective. It's got great perspective, and all of it is wrong, right? Because the vanishing point for the gears is like down there somewhere. The vanishing point for the runway is up there. There's like 6 vanishing points. It's like failed, except that he succeeded beautifully because all of those vanishing points are related to what he knows he's going to do with this visual information. And that's what makes this drawing super duper dynamic and interesting, as opposed to something that's constrained by one single point perspective. It's why painting from photographs is such a challenge. It's why when I look at a painting by a painter who's working from a photograph, I ask myself, what are you doing here that is either dealing with this problem or not bothered by this problem? And invariably, cool enough, what they're interested in mostly is color. They're interested in the color and the surface. So Julie even told me today, I was like, what do you do with this? She's like, well, I don't paint the colors that are actually in the picture. I make it up. She didn't say it exactly like that, but that's basically what she said. Right? Because she's painting from a photo, unabashedly painting from a photograph. That's fine. Like that, there's no problem. But the consequence of that is it forces you or it enables you to make other kinds of decisions. And this is the power of great old Cézanne paintings done from life, where he's painted the bottom of that jug flat because it sits on a flat table, and the top of the jug round because it's got to have an aperture to pour the stuff out. Whereas if you were in either of those positions, you would never experience it from one point perspective like that. The next time you look at a cup, if the top is round, the bottom has to be even rounder because you're looking down on it, okay? Hockney, again, screws around with this by stitching together the wrong perspective from single perspective fragments. Okay, he's actually subverting this whole rule and seeing how far he can get you to believe it. And as Patrick Kavanagh showed, there are aspects of the physical world we really don't care about at all. We care about shadows, that they be darkened underneath us, but their relationship to each other, we do not care. So here it's like the light is over here, so they all have shadows, but then there's like that shadow up there, which is like another light source up here. There's this like dark hole here, so it's like, where is the light coming from that would give you a shadow up there? There are so many physical inconsistencies in this picture, and you know what? None of us cares. Because the one thing we care about, the thing we know, is that shadows are dark. And they tell us where something is locally in space. That's what they've captured, and that's all you need. Everything else you can manipulate to make the rest of the picture work. Who are these two guys? Do you remember? You weren't born yet. George Bush and Dick Cheney. Okay, so it turns out, I know now we've got someone even worse, but sorry. Okay, it turns out that is George Bush. All of his facial features, there's just glasses on top. Right? Because, of course it's George Bush and Dick Cheney. Who else would it be? You already know. You get all lazy on me. You don't do any more looking. You've done as much looking as you need to tell me who it is. Okay? Because vision, what you see, isn't just what hits your eyes, it's what you know. And I'm going to end with one little tidbit, which is about this drawing that was purchased. It's a little washed out, but it was purchased by a very refined connoisseur at Harvard in 1945. And it's a drawing that was sold to Harvard as an original Matisse ink drawing. And the connoisseur was like, that is a rare find, we're going to buy it right away. 15 years later, it was so obviously a forgery that anyone looking at it was like, how could you ever have been duped? And it's fascinating because the drawing looks a lot like the 1940s actresses of the time. So people who were looking at this Matisse drawing were thinking, Matisse makes drawings of beautiful women. Who are the beautiful women? I'm going to do a forgery of a beautiful woman where everyone's going to be like, it's a beautiful woman. Right? Drawing what you know. The actual Matisse drawings, they don't look anything like those actresses. Okay? And to a trained eye now, it's so obvious what the forgeries are. And I use this as an example for all you aspiring art students to just give you a gentle nudge to say, you don't have to try and have a style. You'll have your style all by yourself because you can't help it. Even when you're trying to do a forgery of a Matisse, you can't help having your style that is imbibing what's in your local world and your environment. The real challenge is, like, what's the medium? What do you want to say with that style? So don't fret too much about coming up with your own style. You'll do so without trying. So to recap, I told you I had 4 chapters where I tried to stitch together this idea or flesh out this idea that the brain is a medium, and if we understand that medium, we can understand something about how that medium allows us to encode, store, and transmit information, just like any other medium, like graphic work, like an etching or watercolor painting or glass and silk or video. Those are all choices that we make that influence or shape the kind of message. Our nervous system very much shapes the kind of message that we retain and that we then communicate. And maybe in your own practice, some of what I've said today might influence it or shape it. And if so, I'd be delighted to hear from you. And if in your own practice you've made a discovery of something that you think is really cool and works and you don't really know why, tell me about it, because you've probably made a real discovery that may actually help me understand something about how the brain works. And so with that, I want to thank you for your time. Nobody has any questions. We can go for dinner? Oh.
Along those lines, possibly leading to some kind of discovery, I noticed that in a space, Minnesota, for those soundproof rooms where they use equipment, being there, I noticed that without the sound input, I had very degraded ability to track motion. That I guess that dorsal space.
Interesting.
I can see texture, color just fine.
Oh, that's
but
cool.
once there's moving parts to track or low light.
I'm going to tell them. So the observation is in a soundproof chamber, it's called an anechoic chamber, where vision is still possible because you've got light. It seems to have a selective impact on your ability to track moving stuff, but doesn't have an impact on your ability to identify the stuff out there. I've never heard of that. It sounds totally plausible and real. I think it's super cool, and I will go home and do some homework. Yeah.
The people with Asperger's or autism, does their brains work the same way as you just described? Or are there differences?
So the question is about people who have Asperger's or autism. Do their brains work similarly or different than the way I've described? The question is a very complicated one. I once tried to, I'll tell you a funny anecdote. I've told you a lot about how color works in this color interaction, well, and how knowledge influences what you see. Well, I thought, well, maybe people with autism don't carry around all of this burden of knowledge, that maybe they're looking more honestly, more directly. Okay, so I teamed up with Ellen Winter, who studies gifted students, gifted kids in Boston College, and she got me permission to go to the Higashi School just outside of Boston, where it's a school for kids with autism and Asperger's. And I wrote a protocol, we got approval, it was like months of work, and I went to go and test to see, did they do color matching sort of better, more accurately, more veridically? Like in that cube I showed you, would they have used gray paint or would they have used yellow paint? Right, that was my question. Very simple question. And I showed up and the administrator saw me walk in with all these paints and she just lifted her eyes and was like, really, honey? Okay. And she walked away, she covered everything with plastic. These kids were so sick. There was so much heterogeneity in the group. It's like getting an instruction across that says, could you paint this patch here, over here? It was like, no, it's not good. Just got no data. It was like, I have no idea. It's the short answer. And I think partly what's happened is the narrative that we have of Asperger's and autism has lumped this all into one thing that we want to neatly put on a shelf over here, that they do this thing like this, and once we've figured it out, we'll have cured them, we'll give them a pill, and it'll all be secured. I'm not saying that's what you're saying, but I think in the neuroscientific community, it's often treated that way. What I take away from it is, no, there is lots of diversity. There's lots of, you don't need to go to autism to get diversity. We got diversity in this room, which I'm sure has some autistic people in it, but them in, everybody in, we got lots of diversity. Everybody thinks they're normal. Yeah, you know, I'll show you how not normal you are. Case in point, I don't have stereopsis. I don't have stereoscopic depth perception. I'm an alternating strabismic. I only ever look out of one eye at a time. I had no idea until I was in graduate school. And then I was a control study for someone who studies stereopsis, and they were like, why are you screwing with my experiments? And I was like, I'm not. They're like, well, you said you didn't see any of these things. I was like, I don't. Then I got tested. It was like, sure enough, I don't have stereopsis. Then I developed this theory that maybe lack of stereopsis actually helps you if you're an artist representing something on a two-dimensional canvas, because then you aren't constantly worried about the fact that it's two-dimensional and all the monocular cues to depth are really vividly apparent. And we actually collected some data here at CCAD. Turns out that art students have much higher diversity of optic and ocular and viewing behavior abnormalities. But I don't think of them as abnormal in a pathological sense. I think of them as insightful. Yeah. So I'm sure autistic kids are insightful, just in the same way that anybody is, but yeah.
Does the black and white movement, is that more primitive based on tracking, right?
Yes, so that dorsal stream bit, that is more primitive in the sense that, like, for example, cats don't really have color vision.
You don't need to see the color, you just need to see.
Exactly, and the movement is encoded in value relationships. I hesitate a little bit to say primitive because, like, I had a cat for a while, for 12 years. There was nothing primitive about her. Like, she knew exactly what was up and where it was and had me beautifully trained. And as far as I'm concerned, she was like, you primitive creature who works all day to give me food and warmth. She knew exactly what was going on. Anyway, yeah.
Earlier you brought up that the ganglion cells, you could tell what you're looking at just by the readings of it.
Mm-hmm.
So like the applications of that, couldn't that be like used for virtual reality or Google versus virtual reality features?
It is, and it is currently being developed in that way. So there's a company, Oculus, which you may have heard of, they employ an entire team of visual neurobiologists to develop these tools. Google has a team as well. I mean, all of these AI people have these groups.
Those same signals translate the same for recalling the image as well as actively seeing it? Or is it a different signal?
Are the signals working the same for recalling an image versus seeing it? The short answer is kind of. So if I look in your brain, this was discovered not too long ago. There's a little patch I showed you, that little patch of brain that responds to faces, for example. So Nancy Canwisher did this genius experiment. She discovered that little bit of brain. She showed that every time I show you a face, it shows activity. So then she said, I want you to imagine a face. Okay? And now imagine a place, and now imagine an orange, and now imagine a face. And she had people do this. And she could then look at just the brain scan for that bit of brain and read out what you were imagining. Okay? So in some sense, the answer is yes. And I take it one step further and say, how could it not be? We don't have any other bit of brain. I mean, there's no other thing. It's like, this is it. This is what we got. This is like, seeing is imagining. That's what I mean when I say, all of this cognitive information that's instructing what you're seeing. It's like a big old mishmash of stuff that's... So the way I think about vision is much less like signals hit your retina and then they get run up to the LGN and then they get run up to the cortex and then ding, 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 I see you. Like, I don't think that's what's happening. I think what's happening is you have everybody connected to everybody. It's more like soup. There's like stuff all influencing everything in that network. And then some vision happens, some light hits your retina and it changes the configuration a little bit. So like if the signals are really potent and you're expecting them, then the whole thing goes, yeah, there's a face there. If you're like really preoccupied over here and the signals hit, you kind of ignore it. You really don't see it. One more question and then Julie wants dinner. Dean Taggart. Excuse me.
Brain, so your focus is the artist, is it mostly left brain? Because from what I
No.
read, like we were saying, general people who are artists and stuff.
No, wrong.
Is the left brain and people who are right brain, they're going to be
Wrong.
divided.
Great cartoon. Wrong. Wrong. No, it's a very well trotted out cartoon that we think that they're right brain dominant people that, I can't even remember which way it goes, but they're left brain. I think the right brain is supposed to be artists and the left brain is supposed to be not. They're artists who fall in both camps. What it is true, what you were pointing to, is there are very clear asymmetries in the cortical hemispheres, okay? And those asymmetries fall along, for example, face perception is dominated in the left hemisphere, language processing is dominated in the right, I can't remember. I should know, right? It's the left, it's the right, it's left, it's the right, it's the right, it's the other one, okay? Color is slightly biased for the anti-face area, but there are all these asymmetries. Curiously enough, we don't see those asymmetries in monkeys.
Okay, so in that case, that picture, especially for people who are not good at STEM, but just because with the job, with the economy, is that now people who are good at STEM, they're the ones who are favored. So people who are not STEM fields feel left out, they're discriminated against. So in the future, is there technology where you can wire your brain? If you're not good at STEM, you go get a brain surgery to make you a STEM genius.
Oh, so you're advocating brain surgery to realign your brain dominance? I think it's a more likely strategy that we rewire society so that they can acknowledge the benefits of the people who work in a way that doesn't fall in STEM fields. But with that, thank you for your attention and